Okay, thank you for the introduction. Good morning. My name is Erice. I'm a postdoc at Northwestern University. And I'd like to echo what David Kaplan said on Saturday, that I'd like to thank the organizers for allowing us to present such fringe ideas at this conference. And using those ideas to test quantum mechanics using interferometry. All right, so in undergrad, I learned the interpretation before knowing what it was. And one of the issues that people take with the Copenhagen interpretation is this ad hoc hypothesis of the wave function collapse. And the other major issue is that it's ambiguous about what an observer is. Einstein famously took issue with these two forming issues and famously put, could the wave function be collapsed by the observation of the mouse? To which Bell added that, or whether the wave function of the world awaited the appearance of a physicist with a PhD before collapsing. So this led to the field of quantum foundations research, and arguably the most notable and most famous example is the EPR paper from 1935. Building on that, there were Bell's theorem and the Copen-Specker consensuality in the 1960s. And subsequent efforts led to the formation of the 2022 Nobel Prize in Physics. Now, what I hope to convince you is that this is still a vibrant and interesting field, as Sergey and David have plentifully motivated. In particular, what I would like to talk about is testing the many worlds interpretation in the context of nonlinear quantum mechanics. So the many worlds interpretation was proposed by Hugh Everett in 1957. And according to that, there's no wave function that collapse that occurs. And instead, what happens is that any possible outcome exists in a series of universes called multiverse now. And it's shown in this famous cartoon where the universe splits in half, where the famous Schrödinger's cat is alive in one branch of the universe, but not the other. Now, the notion of multiverse has gained a little bit more traction because this theme recurring in fields like string theory and inflationary cosmology. But despite its weirdness, one thing most people agree upon is that we need a fundamental theory that can reconcile quantum mechanics and gravity. So it would be really great if there was an experimental platform which could not just study the interplay of quantum mechanics and gravity, but also test foundational questions like many worlds interpretation. Now, fortunately, such a platform exists known as interferometry. Now, of course, many of the experimentalists in this audience know that these types of experiments are extremely challenging. And the big question is interferometry competitive enough? Well, let me give you a few examples to suggest that is the case. So back a little while ago, at a 10-meter atomic fountain at Stanford, it was demonstrated that you can create superpositions at the half-meter scale. In the same apparatus, people managed to measure curvature from a local proof mass using the same interferometer. The same apparatus was used to test the equivalence principle down to 10 to the minus 12 level. And as a upgrade to that interferometer, we're currently constructing a 100-meter interferometer in Fermilab, which I'll talk about shortly. And finally, I'll just mention that interferometry has also been used to perform the first quantum measurement of the big G, Newton's gravitational constant. So hopefully these examples will convince people that interferometry is not to start asking these questions experimentally. So what is an interferometer? It is essentially the atomic equivalent of the optical Mach-Zehnder interferometer. The Mach-Zehnder interferometer, you note that if you cause a slight imbalance in these two arms, you get a change in the intensity in the output ports, and you can turn this into a very sensitive position detector, like LIGO does. Now, in an atom interferometer, the roles of matter and light are reversed, where we're using matter waves instead of light. And here, the quantity that we're measuring is the acceleration, little g, over here. So that these two pictures, these are very analogous to each other. So before proceeding some of the details about atom interferometry and how it works, let me first establish a little bit of formalism, because these diagrams keep coming up over and over again. So You can see a cartoon and a space-time diagram of what an atom interferometry looks like. We split an atom into two paths, reflect them, and then we combine them at the very end. Equivalently, we can also write this diagram is in the lab frame. The one on the right is in the freely falling frame, and they're both equivalent. But for this particular talk, I'll focus on the left one because the masses that we're sensing from are stationary. Okay, so a little bit of the atomic physics. The atoms that we use in our experiment are strontium. Here's the electronic structure, where we have a strong electrodipole transition at 461 nanometers and a weak transition at 689 nanometers. So both of these are used to cool the atoms down in successive stages. And then finally, we have the interferometry lasers themselves, which do the splitting and the recombining. First is the 698 nanometer transition at over here. And one of the nice things about this transition is the very high lifetime, which is crucial for gravitational wave detection. In another apparatus, a 2-meter fountain at Northwestern University, which we're also building in parallel with this, we're going to be using the 2-photon drag transition. I'll briefly discuss both of these experiments very shortly. So what happens when you're hitting these with these interferometry lasers? So basically, if you have a two-level system, you resonantly excite this at the, let's say, clock transition, you get lobby oscillations. If you apply a pulse that's part of the cycle, you get an equal population of excited and ground state, which effectively acts as a beam splitter. If you use double the pulse length, you end up with a mirror where you reverse the populations acting as a mirror. Here, basically, absorption and stimulated emission are at play, and this is what allows us to couple the internal and external views of field. In other words, to control the momentum of the atoms. So if an atom in the ground state absorbs a photon, it gets excited and gets a momentum kick. Similarly, if an excited state atom absorbs a photon, it emits two photons in the same direction and gets a momentum kick in the opposite direction. So, as kindly when we advertised yesterday during the gravitational wave session, I'm working on Mavis 100. So unfortunately, but this is not about gravitational waves. This is about testing models on the campus. So, but anyways, here's what we're doing with the apparatus. We're building this 100-meter vertical shaft at Firm Lab. Here's that on the right. You can see a photo from the top of the shaft. So here's a CAD rendering of what the instrument looks like. We have the laser lab at the ground level. We have an atom source that is close to the ground level. 50 meters below that, you have a second atom source. And 50 meters below that, you have another atom source. Here's a zoom in of one of the atom source enclosures and how it interfaces with the atom interferometry vacuum tube, where the atoms are prepared and shuttled in and then launched upwards. Now, the reason we have 3 of them is because we can operate this in multiple different modes. For example, in this mode, we drop the atoms from the top and the middle source, thus allowing us the maximum interrogation time. Here, we launch the atoms from the bottom and the top source upwards. This maximizes the baseline at a little bit of cost in terms of the interrogation time. Both of these are used for gravitational wave detection and scalar dark intersection. And then the third one, where all right, so in the last one, we launched 2 isotopes of strontium from the bottom atom source only, and this allows us to detect a vector growth pattern. All right, so I'll just say a few words about how to detect gravitational waves. Essentially, similar to LIGO, except you trade one spatial degree of freedom for a temporal one, which means that you measure the light propagation time across this baseline using 2 stopwatches, which are optical atomic clocks, which are the best clocks we have. Here's the blue line here represents where we are now in terms of our current technology, and after the instrument has been fully optimized, we expect the sensitivity to go down to this level over here. Okay, so as I said before, there's a parallel interferometer at Northwestern that we're building. Here's a CAD model of it. The nice thing about this apparatus is that this is designed to test gravity from source masses. So we have this nice translation stage. Here's an example where we bring up really big masses in a very precise way. So, and the types of physics we want to study with this is measure big G and test the inverse gravitational inverse square law. The main point I want to make here is that MAGIS was not originally designed to test gravity from terrestrial source sources. But hopefully, combining the expertise of our lab with MAGIS, we will be able to test nonlinear quantum mechanics to unprecedented sensitivity levels. But on the flip side, we think that we can commission the smaller experiment sooner, so we will at least be able to set some leaper bounds with this apparatus. Okay, so an average interferometer can be operated in many different ways. The mode that we operate in is the so-called radiometer mode. Here's what it looks like. So we have our shaft at Minos, where we have the 100-meter count. And let's say we prepare atoms in the middle atom source. We shuttle them into the vacuum tube, and then we launch them up, and here's the space-time diagram. At the end of the sequence, we get an interference pattern from the two ports, which is the dimensional CCD pattern, and you extract a phase that corresponds to the mass of this object that is being next to the interferometer. Now, in principle, this works, but there's two factors to consider. Is that this phase that you're measuring is swamped by the Earth's gravitational field, so detecting this tiny mass is going to be very challenging. Second is that you're susceptible to systematic errors coming from the laser phase noise and vibrations. Now, it turns out that there's a very clever scheme for solving these problems, and what you essentially do is that you prepare atoms in this bottom atom source, and then create a second interferometer. And then once again with the second CCD camera, you image the ports again. And then you measure this differential phase with delta phi. And that hopefully cancels out the Earth's gravity and the other systematic errors in common mode. Now, how do you get this phase? Over here, what does that phase exactly mean? So let me take a slight detour into how this phase is actually computed. So, okay, so here's your interferometer. Here's a Lagrangian for the interferometer, corresponding with terms including the position and velocities of the upper and lower arms of the interferometer. And the term that's going to be the most relevant is this gravity gradient, del G, del Z, which will be the most relevant one here. Now, you can write down I've excluded terms that involve rotation of the Earth because we actively rotation compensate by tipping and tilting these piezo-based mirrors to change the laser where you be pointing as the atoms are in flight. So in this simplified version, you can write down the phase measured by this interferometer in such a way where the most relevant term is the middle one, the propagation phase, which is essentially the integral of the Lagrangian that I just showed you. And once we turn the crank a little bit, we end up with this expression over here. And as I said again, the most relevant term is the gravity gradient del G del Z over there. You don't need to worry about this term. The first one, as I said, in the radiometer mode, that just cancels out the interferometers and common mode. Okay, so and here are some nominal parameters that you would expect for this type of gauges. Okay, so why does this cancel and why does this del G del Z give us some non-trivial contribution? Well, let's take a closer look. So again, once again, we have this source mass over here next to our interferometer. And let's plot the gravity coming from this fruit mass along this axis and dash thread. That's where the atoms are confined to travel. That's shown in the blue curve here. But for an instrument like this, what really matters is the projection of that force along this axis. So that's shown in orange over here. And note that this is simply a modulation of the Earth's gravitational field of 9.8 meters per second squared. And that modulation peak is of the order of 10 to the minus 9g for a mass of 5,000 kilograms. Now, as I said, the quantity that's most relevant is the del G del Z. That's what we're measuring over here. And that quantity is scaled as 1 over the distance cubed. This is, I'll just borrow this expression again in future slides. So one thing to note is that this del G del Z peaks at the location of this mass, but at the bottom over here where we have our second interferometer, it almost goes to zero. So essentially, that's the only term that's surviving, and hence we know that we're sensing from this mass alone, and not no other effects. Okay, so to build on Surjit and David's excellent talks, I just want we're trying to test nonlinear quantum mechanics. And as he pointed out, there's these modifications in the electromagnetic version and the gravitational version given by these expressions over here. I apologize for the sloppy notation. Oh, okay. Oh, sorry. I just copy and pasted. All right. So basically, one nice thing about this proposal is that experimentalists like us can quickly go in the lab and put down to existing or near future technology. And that's exactly what happened with the Shishkov group, where they used a series of classical quantum bits to control classical voltage, and they were able to set bounds on epsilon gamma at 10 to the minus 12 level. And shortly after that, as we talked about, in the ion interferometer group at Berkeley, they were able to place in the tighter bounds. Now, those of us who are in the business of measuring gravity, we're more interested in this parameter epsilon g. But it turns out this kind of experiment was already done in the early 80s by Page and Gaukar. And inferring their experiment, it turns out this epsilon is at the level of order 1. Now, we think we can do a much better job. It turns out that the first atom interferometer was demonstrated by Kasevich and Chu back in 1991, which was after this. And since then, there have been a lot of atom interferometry literature considerably. So we think we can improve upon this man by almost 6 orders of magnitude. So what they basically did was they took took a torsion balance, where in the classic Cavendish experiment, where they used a quantum bit not sure if that was a term back then, but they used the decay of the cobalt atom, cobalt 60, to serve effectively as a qubit to determine where to place their mass. So we're trying to do something similar in Magus over here, where we have 2 positions of the masses we can put them at, d far and d near. And if you write down the Euclid's wave function and use a quantum random number generator, such that if it's come spin up, you place the mass further away. If it's spin down, you place the mass nearer. And then what your atom interferometer would essentially sense is a phase shift corresponding to this gravity term, except the term corresponding to the near one will be suppressed by this factor of epsilon g. And that's the quantity that we want to place bounds on. Okay, so our ability to sense tiny changes in delta phi is set by the phase resolution that scales as 1 over the root of the number of atoms in our cloud. So using some nominal parameters and taking a very conservative estimate that we want our signal to be at least a factor of 10 above the phase length score, and plugging in these nominal parameters, we estimate that we can measure epsilon g down to 10 to the minus 6, which is a 6 orders of magnitude of the previous estimates. So that essentially brings me to the end of my talk. So here's the summary. I have hopefully convinced this audience that interferometry is a very valuable tool in studying not just gravity, but also quantum mechanics, and more importantly, the foundational questions. What we would like to do is repurpose Magus 100 to test nonlinear quantum mechanics in a regime that was tested for. And hopefully, we might be able to commission this smaller bound, albeit with lesser sensitivity sooner, so that at least we can place weaker bounds on epsilon g. And once Magus is fully operational and operating at peak performance, we will be able to exceed the existing bounds by almost 6 orders of magnitude. So with that, I'd like to conclude the talk and thank all of our collaborators at Magus, our team at Northwestern, and a special thanks to David and Surjit, who helped not only for just coming up with this proposal, but also for offline discussions that make such complicated concepts accessible to experimentalists like us. So thank you for your attention.
there a reason to use a fountain interferometer over a lattice interferometer?
So the lattice, the problem is that the lattice, the lasers that you use to generate the lattice are sitting in the lab somewhere where there's vibrational noise and all types of other noise. So that could leak in and screw up your gravity wave measurement, which is notoriously sensitive to vibrations. So that's one. And the second reason is that we want a common mode cancellation between the two parts. So let's say we forget about vibrations for a moment, and let's say that we take two lattices and put them on two different satellites. You have to make sure that you have to make sure that you have to do painstaking efforts to make sure that that your laser noise that you're using to interrogate this, it cancels properly in common mode, because you have to worry about issues like the laser being diffracting and all that, and we can, I think in this geometry we can do a pretty good job of controlling those systematic errors.
Quick question, how close can these test masses come to the atoms in front of these?
So in this particular one, I would say about, sorry, I apologize, I know I'm measuring at 3 feet. And in gauges, which is a meter, I guess. So in gauges, I would say about like conservatively 2 or 3 meters, which is, I think, what in my estimates, I think I use 3 meters is the closest.
More questions? Yes.
Okay, so there are methods to surpass the short noise limit that you want to use?
In the future, yes. It's these techniques are being worked on in the Cascade group right now. They're trying to perfect this further. I think they have some sort of a record of 30 dB of squeezing. So sometime in the future, yes.
So how do you study atoms?
Yeah, so there's an optical lattice that's formed in this like a bow tie shape. That in this middle there's so basically what we do is short one laser beam. So we effectively think of this as one laser beam from the top to the bottom, and then the frequency of one is a sharp with respect to the other. That corresponds to a velocity of the lattice. And then once the atoms achieve, so the atoms essentially just pop into this like lattice elevator. You go up, and then once the atoms reach a sufficient velocity, you just turn off the lattice, and then the atoms are released.